Welcome to webinar 5. So this is our 5th webinar in our series here at Osprey. This one's going to be focused on data analysis. So understanding some of the metrics that go into all of our data and how we can tell when our data might be incorrect or when we need to do something to help our data. I'm Jaden Berger. I'm a research and development engineer at Osprey, and I will be walking us through this webinar. So for today, we're going to talk about two major sections in our data analysis. That's going to be our energy calculations and our emission calculations. Then we're going to talk about reviewing a level 2, which is kind of in our data processing apps. So what we call level 2 is what produces an ISO report. And that could be a really helpful tool in reviewing your data. And then we're going to just briefly look at some standard values that you would expect in an operational LEMS, so you can know if your LEMS is running correctly or not. So it's super important that we understand what we're doing when we're doing our data calculations, understanding how it's calculated, what ranges are reasonable. This means that we can actually understand our results, which means we can have confidence in the data that we're reporting. And that's really important, especially if we're reporting data to clients. We can know when something's gone wrong and then understand what we need to do to fix it. And we can really understand why each part of the test procedure in ISO is so important and why maintenance is so important. So the goal for this webinar is that we understand the data enough to review results, find errors, and fix metrics. There are a lot of calculations that go into everything, so I'm not going to go into every single equation that exists, but I'm going to try and give an overview of some of the bigger metrics that we look at. And if you have any questions, feel free to email me or ask at the end of the webinar, and I can try to help out. Okay, so energy calculations, that's our first big one here. So that basically involves everything that you write down in the data sheet. So energy calculations can be done without any emissions collections. The main one that we think about with energy calculations is going to be our thermal efficiency. That's the thing that we report for our ISO tier. But basically, we're taking temperature and mass measurements, and we go into data processing, and that gives us thermal efficiency, charcoal mass productivity, firepower, cooking power, burn rate. And then eventually we get our performance tier for thermal efficiency. So let's start with the big one of thermal efficiency. So you might have noticed in your report, there are two thermal efficiencies. There's thermal efficiency with char and thermal efficiency without char. There's a whole discussion in the cookstove world on which one should or shouldn't be used. I'm not going to go into that discussion. But it's important to understand the differences between them, just so that you can inform your clients later of what's the difference between them, and you can understand why there is a value difference. So our numerator on both of these is going to be the same, and we're going to actually see this numerator later on, so I'm going to spend some time on it now. So this top part of our equation is going to be useful energy delivered. So that is the amount of energy that actually made it to the pot. So really we want this top number to be as large as possible, because that means a lot of energy actually made it to our pot of water. So the more energy makes it, the more thermally efficient it is. So this first part here, this is saying how much energy it took to heat up our pot of water. So this is the specific heat of water, which is basically how much energy it takes to heat up water by 1 degree, the mass of the water we're heating up, and the temperature change. And then what we add to that is how much energy it took to evaporate water. So during a test, you'll notice that your pot is lighter at the end of the test because some of your water has evaporated out of the pot. That took energy to do, and we can actually calculate that by the change in mass times this, which is the latent heat of vaporization, which is determined by the ambient pressure. Now, where thermal efficiency with char and without char vary is going to be this bottom section here. So without char, it's a little easier. This is just all of the energy that you used from the fuel. So the mass of your fuel times the effective heating value of your fuel. What we do when we say thermal efficiency with char is we say, okay, so we input all of this fuel, but at the end of the test, we had a remaining pile of charcoal. And that wasn't really calories that we used in the stove. That wasn't wasted energy because it's still here. So we're going to subtract out that remaining energy from the charcoal and kind of give credit to that remaining energy. The thermal efficiency without char is saying, well, we put all of that fuel in there, we put all of that energy in there, and we're not guaranteed that people are going to use their charcoal as an additional energy source later on. So we're just going to count it as wasted calories or that used calories. And so we're just going to say we used all of the fuel and there was nothing remaining. So I put a list of all of the inputs that go into our thermal efficiency. A really great way to check when your values are wrong is to understand all of the things that go into your values, and then we can go back and check those inputs and see if they're reasonable. Most of the time, there's something just a little off in the inputs that can really drive our metrics to really odd numbers. So all of the masses and temperatures, your ambient pressure, this is pretty important. So depending a lot on mostly your altitude, it's either going to be easier or harder to evaporate water, this latent heat of vaporization, very dependent on this ambient pressure here. These three final ones, so the higher heating value of your fuel and charcoal, the moisture content, and the lower heating value conversion factor, these all go into your effective heating value. So your effective heating value is basically the exact amount of calories in the actual piece of wood that you have. So this higher heating value, we can grab that from something like literature. And that's saying, like, ideally in the wood, if there was no moisture in it and everything was perfect, that's our value. But we've got some other factors. Our wood is obviously not 0% moisture content, so we have to factor in our moisture content. And we also have to figure out this lower heating value conversion factor, which is going to be dependent on the elemental analysis of your wood. You can sometimes find this in literature. There's a standard value that we use for wood. If you're using other fuels, you may have to do some literature search or do an elemental analysis, and there is calculations for how to do that in the ISO standard. So what's the normal range for thermal efficiency? We expect around between 15 to 60%. I know that's a pretty large range. With charcoal stoves, because of how we test them, we can sometimes see that the low power phase is actually even higher than 60%. I've seen into the 70% range. So higher or lower than this range doesn't automatically mean that it's incorrect, but we should examine the values and really think does that make sense? Especially if a wood stove is showing super high, above 60%, we should really think, does that make sense for the stove design? Or is there an error? And then if we're getting a thermal efficiency below 0 or above 100, that's absolutely wrong. The physics, we can't do that. That would say that we put more energy into the pot than we put into the fire, which just doesn't make sense. So what do we do when those values are wrong? My first step is always looking at the inputs, like I said. So this is why I'm going through all these equations and saying what all of the inputs are, is because then I can look through. The first step I'm going to do is look at my digital data sheet that I've written and my written data sheet and see that those inputs are exactly the same. Sometimes it's as simple as something was just typed incorrectly, and that's a really easy fix. If I can't find anything that way, then I'm going to pull up a similar test. So maybe I've done a test on this stove or a similar stove and had results that I trust. And then I can compare my inputs and outputs with that stove and see what varies between my inputs, what's throwing it off that's making this one 80% and my trusted test at 40%. Some big ones to pay attention to is the water evaporated. So you're changing mass of your pot. If there's a ton of water being evaporated, if you've evaporated 1 kilogram of water, which would be impressive, that could be what's driving a really high thermal efficiency. Charcoal produced is another one. If you have a really large amount of charcoal produced, you're going to have a really big difference between your thermal efficiency with char and without char. And then finally, how much fuel you used. So if you used a ton of fuel, that's going to drive your thermal efficiency down, especially if that was entered incorrectly. So we want to see if anything was entered incorrectly. We might want to go and talk back to whoever did the test. Sometimes things went wrong. For example, some water spilled and that wasn't recorded, or the water boiled over. Sometimes if there's too little water and it's a really high power stove, if a lot of that water boils off to where there's almost no water left, that can really throw off the test. Or sometimes some of the leftover charcoal pile, some of that is actually wood and it's counted as charcoal, and that throws off the test as well. And thermal efficiency with char is only going to be valid for wood stoves. You'll just get a blank metric for your charcoal stoves. Okay. I apologize if I go through any of these kind of fast. There's several metrics to go through. Again, we're going to post these slides and the video is recorded, so you're always welcome to go back through it or email me to ask any questions, and I'll try and leave some room for questions at the end. So char energy and mass productivity is essentially our ratio of how much charcoal was produced and left over at the end, divided by how much fuel we used. So if we had a char mass productivity of 50%, that would mean that 50% of the fuel that we put into the fire was left over as a charcoal mass at the end of our test. So that's pretty high. That's a lot of the fuel actually just is left over as charcoal. For energy production, that's that same equation, but you're just multiplying it by that effective heating value for charcoal and fuel. We would expect a normal range between 0 and 50%. 50%'s probably on the high end, unless maybe you have a biochar stove and that's the intention of your stove. So of course, 50 doesn't mean it's wrong, but again, we should check our equations. Luckily, with this charcoal mass productivity, there is a visual indicator, and that's just the pile of charcoal you have at the end. So if you get a 50% charcoal mass productivity, you should expect that you have a pretty sizable amount of charcoal left in your stove at the end of a test. And so if you don't have that and your charcoal mass productivity is reading 50%, then maybe there's an input that's incorrect. You'll see that all of our energy and emission calculations, they're all connected together. So one incorrect input is going to throw off several metrics. So for example, if we have a really high char mass productivity, that's going to mean that our two thermal efficiencies are super different from each other because one is dependent on that charcoal. So we really want to make sure that we're accurately measuring our charcoal at the end of a test. If it's incorrect, then we're going to have one thermal efficiency that's probably correct and one that's way off. Again, if it's below 0 or above 100, because this is a percentage, is going to be wrong. So there's something that you need to fix. And for charcoal stoves, there is no char mass productivity since you're starting with charcoal. So it's only valid for wood stoves that are converting wood or other fuels into charcoal. Okay, firepower. So firepower is basically the strength of your fire. So what we're hoping for in an ISO test is that our high firepower test or high power test, that's going to have our highest firepower, and our low power would have our lowest firepower. This is essentially just how much energy was used divided by the length of time it was used over, which should be 30 to 60 minutes in an ISO test. And for burn rate, it's just the mass of fuel used over that same time period. For firepower, we're expecting wood to be around 1 to 10 kilowatts and charcoal to be about 0.5 to 6 kilowatts. Charcoal stoves tend to have a bit lower range. These are for more personal cook stoves than for institutional. Institutional cook stoves may have a higher firepower for those large pots. High firepower is correlated with higher PM emission rates. So if you're really blasting your stove, you can expect to have higher PM emission rates and higher emission factors, which goes into our tiers. So if PM data is uncharacteristically high, I would check your firepower and see if that's actually a reasonable operating power, or if maybe your firepower was way higher than you would expect anyone to use it at, and then you can bring it down. Okay, so similar, we've got cooking power. So firepower is generally all of the calories we used over time, whereas cooking power is all of the energy the pot actually experienced over time. So you can, if you have a low efficiency stove, you can have a really high firepower and a really low cooking power, which would mean that we had a really high energy fire, but only a small amount of that energy actually went to heating up someone's food. So we can see this top bit again. This comes from our thermal efficiency. Remember, this is our useful energy delivered. So the amount of energy that our pot actually saw, divided by the time. And we expect this to be lower than our firepower. It should correlate with your thermal efficiency. And so we're expecting around 0.25 to 6 kilowatts. Okay, so emissions calculations, this is where some of the math is going to get a little crazy. I will try my best to make it as easy as possible. Emissions calculations gets a little crazy because everything starts getting interconnected. All of our inputs and our outputs from energy calculations goes into our emission calculations. So really the first step is those energy calculations and making sure they're correct. If your thermal efficiency from your energy calculations is way off, that is going to impact your emissions calculations. So we might as well correct the energy stuff before we go to emissions. That's going to save us time in the long run. We're also going to take in our emissions data from our sensor box. The background subtraction methods are going to be really important when we're doing our emissions calculations. I'll talk about that in a second. And then the filter data for PM 2.5. And yeah, you can see that a lot is going into our emissions metrics. So it's really important that we're looking at all of our inputs and outputs. This can be where a lot of stuff kind of goes awry. So some of the important metrics are emission factors, emission rates, carbon ratio, and then emissions per megajoule delivered, which goes into our performance tiers here at the end. So first I'm going to talk about emission rates. Here's my attempted drawing on the side here. Emission rates is going to be the concentration of whatever species we're measuring, so CO2, CO, or PM, times the volumetric flow rate in the duct. So here I've kind of drawn our hood with a fire. And what's happening when we're measuring our sample gases is that we've got this red line, that's our emissions from our stove. But we've also got a blue line, which is our dilution air. And so in the duct, those two are mixing together and they're making purple, because red and blue make purple. And so our sensor box is measuring a purple gas. And so several of the steps before we get fully to emission calculations, so several of the steps in our data processing steps are trying to separate back out to the red and the blue, because all we're interested in is the red. We don't really care about the CO and CO2 and PM that's in the room. That's not super important to us. We just want to know what's coming from the fire. So that's why our background subtraction is really helpful. That step is basically looking at the blue before we add any red so that we can subtract it out from all of our readings. So it's really important that we pay attention to that step, that we're really zooming in on our subtraction graphs, because if we're incorrectly doing our background subtraction, then we're either leaving in some of the blue when we're doing our emission calculations, or we're taking out some of the red, so we're not fully measuring all of the red. So it's a super important step to pay attention to. The other measurement that helps us determine blue and red is our flow rate. So that flow grid that's in your LEMS, more dilution air, that's going to mean a higher flow rate. So that's why it's really important that we do our calibrations on our flow grid. And emission rate, that's going to be dependent on time. So let's get into, you can see here, this is where all the math gets a little tricky. So we're going to go through emission rate. We're going to look at concentration, how we measure concentration first. The next slide, we will look at the volumetric flow rate. Concentration is actually, I know there's 3 equations here, but it's actually not that hard because we're already measuring concentration from the sensor box. So our sensor box, we're measuring ppm, or parts per million, of CO and CO2. So that is a concentration measurement. Basically, these first 2 equations here, all we're doing is just doing a unit conversion. So we want our concentration in grams per meter cubed instead of parts per million. So these first 2 equations, we're basically taking our parts per million and converting that to grams per meter cubed, so that's taking in our measurement, molecular weight, of whatever species we're measuring, the pressure in the duct, the temperature in the duct, and the universal gas constant. The pressure in our duct, that's going to be determined by our ambient pressure, so that ambient reading that you take in the lab. And then we're going to subtract the static pressure in the dilution tunnel. This is measured during our velocity traverse. So you should be able to find that value in the data from your last velocity traverse. If you don't have that, then it's probably time to do another velocity traverse. For PM, the concentration is just a little different. It's basically your filter mass divided by the time and the flow rate of your gravimetric system. And that will get us that same grams per meter cubed of concentration. Okay, now volumetric flow rate. This one is not just a unit conversion. This is basically the mass of the gases, mass flow of the gases in the dilution tunnel divided by the density of the gases in the dilution tunnel. So mass flow, I'm going to focus here for a second on these two first things that we're multiplying by. This factory flow cal. So it's a calibration factor. This is determined by the duct diameter. So luckily, we all should have 6-inch ducts if we're using a LEMS. So it's always going to be 15.3 for those 6-inch ducts. So that's pretty easy. That's just going to be default. And then there's this flow grid cal factor. This is also determined by your velocity traverse. So it should be in your velocity traverse data. So I look for that in there. And then we also look at our flow data. So this is the pressure drop that's measured from our flow grid, the pressure in the duct and the temperature in the duct. And then density here, some of you might kind of recognize this equation. It's really commonly used in chemistry. Basically, we're taking the molecular weight of air, which is what which is close enough to what the molecular weight of our gases in the duct are, multiplying that by the pressure in the duct and dividing by the universal gas constant and the temperature in the duct. And that gets us our density. Okay, so carbon ratio, this is a metric that I don't think is talked about that much. It's not something that's required by ISO for reporting, but I would highly, highly recommend it. This is maybe one of the easiest ways to check that your that everything you set up in your system is measuring accurately, and like that you have good quality data, basically. So our carbon ratio is a ratio of how much carbon we measured going out of our system, so how much carbon we measured in our emissions, divided by how much carbon we measured coming into our system, so how much carbon we measured from the fuel that we put into our system. So in a perfect world, carbon ratio would be 1. So all of the carbon that we measured going into our system, we also saw coming out of our system. We don't live in a perfect world, so our carbon ratio it's not always going to be exactly 1. There's uncertainties in measurement. Some things can throw it off, so I'd say an acceptable range should be between 0.8 to 1.2. Anything outside of that range is going to indicate that something is off with your system or with your inputs. So carbon ratio, when people send me their data to check, this is probably the first metric that I look at to see what's going on. This can give me an indicator if things are good or bad in the system. So carbon out basically is we're looking at how much carbon, total carbon, we measured from each of our emission species. So from our CO, our CO2, and our PM. There's carbon in each of those. We can figure out the exact mass of carbon from those. If I tend to see that if something's going to go wrong in our carbon ratio, it's probably our carbon out. There's a lot more that goes into our carbon out. You'll see in a second, carbon in is a much easier equation. So typical things that I'll see that can throw off your carbon out is going to be that your flow rate measurements are off. So your flow grid isn't calibrated correctly, or maybe it's clogged, or there's leaks in the tubing. All of those can throw off your flow rate. It could also indicate that it's not a total capture system. So maybe some of the gases are escaping into the room, or there's leaks in the duct, and that is causing not all of the carbon to actually be measured by the sensor box. There could also be leaks in the sample lane, which would mean that some additional dilution air is leaking into our sample, or some of our sample is leaking out before our sensor box is measuring it. And then finally, our calibration values for CO and CO2. If those are off, that's going to throw off our carbon ratio. Carbon in, that's a little easier to deal with. It's essentially how much carbon is in the fuel that we used minus how much carbon was left over in the charcoal at the end of the test. So it's pretty easy. I would say what I see that throws this off the most is that when you measure your charcoal at the end of the test, some of the pieces of charcoal are actually not fully carbonized. They're actually probably closer to wood. I see this a lot in pellet stoves. This can be hard. Like some of the pellets are actually still wood pellets and they're just a little blackened on the outside. So if we count that as charcoal, charcoal has a much higher carbon fraction than wood. It's 0.9. So 90% of charcoal is going to be carbon, whereas wood, 50% of wood is carbon. So essentially, if we're saying some of our charcoal pile, all of that's charcoal and some of it's actually wood, we're over accounting for how much charcoal is how much carbon is remaining. And so our carbon in is going to be an underestimate of how much carbon actually went into our system. Masses could also just be wrong, and that could throw off our carbon ratio. Or carbon fractions could be off. This is more important for charcoal stoves, so the quality of your charcoal can determine your carbon fraction. So really high carbonized charcoal is going to have a higher carbon fraction than lower carbonized charcoal. So this is something that you can measure to get the exact carbon fraction for your charcoal. Wood is usually pretty consistent. Okay. Emissions factors. So unlike emission rates, our emission factors are independent of time. This can be helpful. So emission rates, they're actually pretty good for ISO because we have the same phase time. So when we have the same phase time, it makes it pretty easy to compare emission rates between stoves or between tests. When we have different phase times, that can make it or harder to compare emission rates because it's a time-based metric. So emission factors can be a lot easier to compare because they're independent of time. It's not super applicable in an ISO testing setting, but you might be doing other tests that don't have a prescribed time. So this is essentially the ratio of the mass of measured emissions for whatever species you're looking at, divided by the mass of the fuel. Or you could do the energy from the fuel, so the mass of the emissions divided by the energy of the fuel for an energy-based emission factor. And ISO, for this fuel-based emission factor, we report it as the mass of the emissions divided by the dry mass of the fuel, so the mass of the fuel with the moisture content subtracted out. But you can also report per wet mass of fuel. That is also a valid emission factor. It just doesn't go into our ISO report. And this one, emissions per megajoule delivered, this is also an emission factor. This is the one you're probably very familiar with because it goes into our ISO tiers. So with this emission factor, we're looking at all of the energy input by the fuel. With megajoules delivered, we're going back to that useful energy delivered. So the mass of our emissions divided by the energy that actually made it to the pot. So you can see that everything's interconnected. This is from our energy calculations. So if this useful energy delivered is off, now not only is our thermal efficiency off and our cooking power off, but also our emissions per megajoule delivered. So all three of our tiers, all three of our performance tiers are going to be off just if this one equation is off. So that's why it's super important that we're checking everything, because one error can throw off all of your data. And I put down here are the tiers for PM and CO, so what we're expecting for megajoules delivered for our tiers. This one's a little harder to kind of check the range, but I will give a method in just a minute of how we can understand if a test is off for these metrics. Which brings me to reviewing a level 2. So in our data processing apps, we have a level 1 app, and that's doing a single test. That's looking at a single test. That's doing our energy and emission calculations for one test. In a level 2, that means we've done all 5 test replicates for ISO tests. And now we are going to average all of those results together, do some statistics, and then there's a nice little button in the level 2 app that creates an ISO report for you. So I'm going to go over that ISO report and how we can use it as a tool to do a final verification of all of our data before we report it to a client. So this is a really nice way to check over everything, understand that all of our tests we can trust before we send it over to anyone else. So step 1, this first page is going to pull up on your ISO report, and it's going to show you the average of a few different metrics, and then it's going to show you 2 other numbers. So it's going to show you standard deviation, which is basically telling you how consistent all of your averaged values are. And then it's going to tell you a 90% confidence interval. So this is saying that based on the data that we used to get this average, if we were to retest this stove, 90% of the time, those results would be in this confidence interval range. So if we have super consistent results, if all of the numbers that we're averaging here are really close to each other, then we're going to have a really small standard deviation, and we're going to have a pretty small confidence interval. So this is really nice. We can see here this green box from this first stove for high power. We've got a standard deviation of 1.1. We've got a really small confidence interval. That means that all of my thermal efficiency with char results for this high power phase are pretty close to each other. That's really consistent. That means I did a pretty good job. of running the test the same way every time. And that's going to indicate pretty high quality data. Now, on this bottom stove here, you can see we have giant standard deviations. So we've got standard deviations of 30%. So that's telling me that there's probably at least one test in this stove too that's probably incorrect. It's way off from all the other tests, and that's giving us this really large range when we're doing our averaging, and definitely need to go and look at our data. In the stove one, I'm going to go back to this yellow box now. This one's a little tricky, and I actually missed it on my first pass of getting this example data. But you can see that our standard deviation is actually not that bad. 5.6 is not too bad for thermal efficiency. But our confidence interval is actually pretty large. We've got about a 20% confidence interval. That's telling me there's probably one test that's a little or pretty significantly off from the others that might be impacting our results here. And I should probably go and look at that test and see what's happening. The reason we want to pay attention to our confidence intervals here is that what ISO does for these tier ratings is it takes the lower, or for thermal efficiency, it takes the lower value of your confidence interval and uses that for its tier rating. That's going to be the opposite for your emissions per megajoule delivered. It's going to take the upper tier of your confidence interval. So basically, even though we have a 60% average, for ISO, they would only be looking at this lower tier of 50%. So sometimes that if you have a large confidence interval, that can drop you one or two tiers in your ratings, which is, so it's important to pay attention to, because that can bring up questions to clients if you're reporting that. And they're like, well, but the average is super high, but because your confidence interval is so wide, your tier is 1 instead of 3. So now we've identified that there's maybe some issues with our data, which means we can go to the next 3 tabs in our ISO report, which is going to be looking at all of our tests for high power, medium power, and low power. So this is a pretty easy way to kind of visually scan all of our results and see what might be different than the others. It's kind of a spot the difference game. So you can see here, if we look at our thermal efficiency for this stove, you can see that for test 1, test 2, and test 3, they're all really similar thermal efficiencies. So that's saying I can trust this thermal efficiency. All these tests had pretty similar results. But then I scrolled further down and I saw that my PM, my emissions per megajoule delivered for PM, 2 of my tests are in like the upper 300 range. And then one of my tests is in the 100 range. So that's like a third difference in my PM results, even though I have the same thermal efficiency. So that's probably something that I should look at. That's going to cause a higher standard deviation and a higher confidence interval. And this could indicate that maybe something was off with my PM, or possibly something in my operating conditions was off, and maybe I need to redo test 1. And then I went deeper. So this is my stove 1, where I noticed that my confidence interval was high. So if I go to my low power, I can see that 2 of my tests are at 63% thermal efficiency, and 1 is at 53%, so 10% difference. So that's why my confidence interval is so high, is that one of my tests is quite a bit different. So that's another thing. It doesn't necessarily mean that test 1 is wrong, but we should probably look back at it, maybe talk about test conditions. Maybe the fire was just smoldering at one point or went out. That can affect our thermal efficiency. Just kind of trying to see why that's different and if we need to redo a test, or if we're fine reporting this, but we understand what happened. Okay, so now we've gone through all of our tests. We see all our values are really similar to each other. That's great. We can now, we're almost done. We're almost ready to report this. Our last thing is checking our quality control. So there's one more tab in our ISO report. That's going to be reporting all of our quality control metrics. Really useful to just scan through this tab. There's going to be a bunch of things that say pass or fail. You want to make sure that all of those say pass. If they don't say pass, that's introducing error into our system. And that can be a major issue, especially sometimes that's unmeasured error, and that can really throw things off. So I know that quality control, like leak checks, they can take a while, but I promise that they get easier with practice. If you're doing a leak check every single day, you're going to get that down to 15 minutes or less. If you're only doing a leak check every month or two, it's going to take a lot longer every time. And in the end, stuff like leak checks does save time, because if you do 5 tests and you don't do a leak check, and at the end you figure out that your system is leaking because all of your emissions are off and your carbon balances or your carbon ratio is wrong. Now, instead of just having to take 15 minutes to do a leak check, you've got to take a whole week to redo 5 tests. Also, all this quality control is required for ISO. So not only is it going to save you time, but it is required for reporting all of these stove tests. So let's start with our leak checks here. You can see here, this is just reporting our leak checks. There's a separate place in the data entry app to actually enter all our values and record our leak checks. But we're making sure that all of our sample is getting to our sensor box, and that there's no unmeasured dilution air added to our sample or leaking out, which would cause our flow grid to measure incorrectly or something like that. And then our drift and bias checks. So that's using our calibration gases for our CO and CO2. That's checking the calibration of our CO and CO2 before we do tests, and checking that our sensors aren't drifting a lot, which can be caused by significant changes in our testing environment or other sensor drift. So we want to make sure that we're passing our bias and drift checks. Our gravimetric, this one actually doesn't take that long. You probably are writing down all of this information already. You just have to enter it for it to go into the ISO report. So basically, we're checking that our balance for our filters is calibrated by weighing it with the calibration weight, checking that that passes. This app will automatically look at the difference in mass of your dirty to clean filter and see if that passes the threshold for the balance that's used. So you have to have enough change in mass to overcome the uncertainty of the balance. So it will tell us if we pass or fail our filter mass threshold. If we fail, that is indicating that we need to use double filters for that stove or for that phase. We're also checking that our gravimetric flow rate didn't decrease by significantly from the start to the end of a phase. So this is just writing down the flow rate reading at the start and end of a phase, pretty easy. And then just recording our desiccator conditions. So basically it's just recording stuff that you've already recorded. And then some of our quality control is automatically entered into our ISO as long as we've entered these values. The app is going to do the rest for us. Our only job is to just scroll through and check that everything passes. So here we're looking at our dilution tunnel flow check. So that's checking that the dilution tunnel flow rate didn't change significantly during a test. Temperature check, that the temperature in our lab didn't change significantly and it stayed within an acceptable range throughout our test. All of this is just kind of automatically, as long as you've entered your temperature, it'll tell you if you pass or fail at the end. It's pretty easy. And then finally, we've got a page on carbon balance. So we want to do a quick scan and check all of our carbon balances. So you can see here, this stove, we had really good carbon balances. They're all around 1. That's amazing. That tells me, okay, I can really trust all of this data now. The carbon balance is good. All of the tests are similar to each other. Our standard deviations are low. This data is ready to go. Now, stove 2, we've got some really funky carbon balances going on. We've got a 2 and a 3. That's crazy. That's telling me this data is not quite good enough yet. So I need to go back and figure out what's going on there, identify what I need to fix. Maybe I need to redo some tests before I can report the data. Okay, it's been a lot of talking. I put this page in as reference for you. So this is some kind of standard operational values and standard test values that that you should know. This can be a pretty good indicator of just that your system's in working condition. So like your gravimetric flow rate should be around 6.7 liters per minute. If it's not running at that could indicate something like a clog. Or your dilution tunnel pressure, your flow grid should be measuring between 0.1 and 0.5 inches H2O. If it's measuring different than that, that can indicate calibration error, or your fan needs to be cleaned, or there's a leak in the tubes for your flow grid, or maybe your flow grid is clogged. With the CO and CO2, you can kind of do a visual check that your calibration values are in the right place by just when you're measuring your room air. These are expected CO and CO2 values. So this can be kind of a good visual check when we're starting our LEMS, that everything's more or less in the right area. Okay, I will end there. This is my email. I would also like to send out an offer to anyone that's doing data, that if you want a second eye on your data before you send it out to anyone, you can send me the data and the report, and I will look it over. This is a service that Opera is offering free for the labs or for any LEMS users. We won't share this data with anyone outside of Opera, but we're just offering this as a way to check your data before you send it out to anyone, so we can identify or help you identify errors or tell you that it's good and you're ready to go. I also added this little cheat sheet for our app. There's some of the named outputs are a little wonky, so I just kind of added what all of those mean. This slide will be published, so you can look at it later. Does anyone have any really quick questions? I know I ran up to the hour here. Okay, I'm going to take that as I did a really great job, and now you understand all of the math, and you're all experts at data processing now. Okay. Okay. got an echo again. So thank you so much for coming to the webinar. We are going to have another one in 3 weeks that will be hosted by Sam Benson and Dean. They will be starting a 3-set webinar series. Each one will be focused on all of the design for specific stoves, so wood stoves, pellet stoves, and charcoal stoves. They're going to do a deep dive into each of those for an hour. So I think we're starting with wood stoves in 3 weeks. We'd love for all of you to come, and I will post this video and slides as soon as possible. Okay. Thank you all so much for coming.
Hey, Jaden, thanks for the session.
Yeah, of course.